This is a remote sensed image from yesterday, and it's actually kind of an interesting situation we have. I woke up this morning to lightning at my house right after a Santa Ana, and in fact, I think the breezes here are still offshore, so we have this kind of remarkable pattern. Of course, we're sitting here right on the edge of the Pacific Basin, and of course, as you know, this is a great place to be a climatologist because, in fact, the global weather generator, to large measure, is over the Pacific Ocean. So I'm going to try to focus on that influence as well as these regional influences that Nigella mentioned just a minute ago. And the other key, I guess, to this talk is the fact that water is part of the story. It's really vital to us in the West, and of course in Southern California there's been the news about the surplus that we're losing from the Colorado River with this failure to negotiate a deal with the Imperial Water District. And it kind of underscores some of the issues that we're trying to grapple here with the regional climate. So without further ado, I want to just go kind of move along. You know, despite the fact that we're going through quite a dry spell here in the last week or so, we had what I would call a very magnificent start to winter in December over the state, and in fact throughout much of the West. The precipitation is depicted here on this map, and it's a little muddy, but this red area are amounts in excess of 200 millimeters for the month. That's well over 8 inches at many stations. I believe San Francisco had a little over 12. Some of the coastal stations in Northern California had much more than that. Many stations recorded 300% or more of their normal December precipitation. Now, this year there's a lot at stake in the West because we've gone through such a dry period virtually over the entire West, and of course as the next few months plays out, that's going to have a big impact on the affairs of water managers throughout the region. By the way, the anomalous departure of precipitation is shown here at the bottom, and you can see that the West is pretty much all green, with the exception of the Southwest, which is a little bit of a surprise. So what we've got here, thanks to Larry Riddle, who's standing in the back, is an animation of the infrared imagery starting in about the middle of November, and you can see the active storms that are crossing the Pacific. They take about 5 days to traverse from Japan to our west coast. You'll also notice that down here in the tropical area, there's quite a lot of heavy convection, which is being enhanced by warmer waters than we normally have. Of course, there's an El Nino that's developed. And one of the things that you'll notice is that in some cases there's actually a feed of this moisture from the tropics up into extratropical latitudes. Generally not that's affecting us. These storms that we're seeing and have seen in December are pretty much cyclones that have not received tropical moisture, but in some cases that moisture is getting across Mexico and into the southeast, which receives some heavy precipitation as well. You'll notice all this activity that's affecting particularly the northern part of the state. I was very impressed in watching the radar imagery through this event and just the persistent nature of this activity. In many cases, stations were receiving, at least the wet ones were receiving 6 inches in 24 hours or more. So On the other hand, when you look at our situation climatologically, this is the mean precipitation has been cobbled together from both remote sensed images as well as rain gauges. We're under the strong influence of the North Pacific High, which affects us with essentially a blanket of descending and rather dry air. So that when you look at us in terms of our water budget, in sort of global terms, well, the very heavy areas of the globe are receiving meters of precipitation per year here in the red shaded areas and these areas of the storm tracks in the western parts of the ocean basins. We're measuring our precipitation generally in units of centimeters because, again, of this influence of a high pressure regime, which, as you can see, inhabits the eastern parts of virtually all of the ocean basins. Well, all of this, of course, has tremendous scientific interest to a climatologist, but there's a great amount of interest because of the impacts it has on our social and economic livelihoods. California's population, of course, has really grown extraordinarily over the last decades. Since 1970, our population is up to 175% of the 1970 census. We're projected to approach 60 million people by 2040. And of course, all of this kind of amplifies the impacts of climate effects. California, of course, has a water system which shown at the bottom here, and it's a little fuzzy, I apologize for that, but it's designed to sort of take advantage of the water that's accumulated elsewhere and transport it and store it and so on. By my rough estimate yesterday, we've got more than 1,200 miles of aqueduct in the state. We actually have only about a year's worth of annual flow storage. I even get seagulls to come to these. It's pretty good. But when you look at the amount of water that we actually develop out of all of the precipitation that occurs in the state, about 200 million acre feet, we're only able to actually organize and develop about 20% of that total. And of course, a lot of it is eaten up by the agricultural sector. I wanted to mention, this slide is out of order, but back to the sort of social setting in California. By somebody's recent count, California actually has the 5th largest economy in terms of the global set of nations here. And by my reckoning, when we look at the economic sectors in California, which are listed in terms of their dollar value in this chart, there's 3 of the top 6, tourism, agriculture, and apparel, that certainly have links to climate. And you can, for apparel, you can look at Larry's Hawaiian shirt back there, and I rest my case. So we've developed, at the encouragement of some of the federal agencies, a program that tries to not only understand regional climate variability, but tries to make this link between the science and some of these social issues like water resources, management, human health, and wildfire activity. And I'm going to show you some excerpts from some of those studies in the following set of slides. By the way, this is that website that Nigella was mentioning. So actually, when you look at the precipitation that we receive in the state, it's very complex. And of course, when you look at it, it looks to some measure pretty much like the topography that's arrayed over the state. And in fact, you can see the huge impact of rain shadows, west slopes, and so forth in terms of our precipitation balance. One of the points that I'm going to make towards the end of the talk is the fact that we really don't know this precipitation budget very well, and that's one of the things that we need to work on in terms of understanding how the precipitation plays out, not only in the volume of water that we get, but its form, whether it's rain or whether it's snow. So one of the impressive things about precipitation is that first of all, it doesn't happen very often. Around here in a good winter, maybe 1 out of every 5 days or so has rain, and most of those rainy days are actually on the lighter side of the precipitation. This is the amount of precipitation recorded in a rain gauge at Nevada City in the west slope of the Sierra Nevada, and this is the fraction of days with precipitation that incurred that particular amount. And as you can see, that as you get up to 50 millimeters or 2 inches and more, those are very rare events. But when you look at the water that's accumulated by the amount of precipitation event, the story is that the heavier events actually have a very disproportionate influence on the water volume. So another way of saying that is that a few storms really are vital to making a good winter in our climate. That is, the very heavy events are really critical in terms of accumulating our water supply. And of course, the other thing is that they have often some negative impacts like floods. And when you think about the California scene, which we looked at in the topography there, California actually has all of the ingredients for heavy flooding. It's got a moisture source. It's not that far away from the tropics and the subtropics. Happens rarely, but sometimes it happens. It has west-facing slopes that give this orographic influence and induce precipitation as air rises over these slopes. And in many settings, such as Mission Valley and such as the Great Valley in California, we've got a lot of flat land, so that floods, in fact, can be pretty devastating. Well, another interesting thing about the precipitation activity here in California is the fact that the time window that we have, the opportunity for storms, is actually quite short. This picture is conveying the time that it takes, the average time that it takes at a given station, and these are actually a set of cooperative weather stations that we've collected data from across the western part of the nation, west of the Mississippi. And the coloring here is the time in days that it takes a given station to accumulate 2/3 of its normal annual precipitation amount. And what you notice in California is that time is something like 120 days or less. Okay, so in other words, a third or less of the year is generating 2/3 or more of our precip. On the other hand, these blue areas here were up to well over half the year. So they get a broader opportunity for precipitation. So when you think about it, the problem is that if the atmospheric circulation isn't behaving itself within that 120 days, that 4 months, we're in for trouble because we've all of a sudden missed our chance. And of course, from an atmospheric dynamicist point of view, what that really means is that the Pacific storm track is only giving us sort of a brief seasonal opportunity to collect these storms that are sweeping across the Pacific. Now, this picture at the bottom left here is actually the fraction of the annual precipitation that occurs during the months of October through March. That is the cool season. And this sort of jet ink blue color over here is greater than 80%. So you notice that virtually all of the California coast accumulates over 80% of its precipitation climatologically between that the 6 months of the cool season. Now, to make my point about the interesting nature of precipitation in the state, what we've done here is we've taken two of the major river basins in the west, the Columbia at the top and the Sierra, the collective west side of the Sierra drainages here at the bottom. This is the annual discharge that would have occurred naturally from both of those watersheds, and it's sort of taken out the effect of diversions and human activities here. And we've got a long record for the Columbia that goes back before the turn of the century. This is 1900, and this goes through 2000. Sorry about the fuzziness on the slides. Our record in California goes back to about 1915 here. And actually, it's before that. It's just the mid-1900 decade. But the point I want to make on this is the fact that when you look at the mean flow volume for the Sierras and you notice the amount of variability, the amount of typical variability divided by the average value for California is about 0.44. So it's the sort of the size of a typical fluctuation over the average. So it means that on any given year, you could be almost half of the mean above or half of the mean below that value. So it's pretty volatile. On the other hand, the Colorado system, that relative amount of fluctuation is only about 0.2. So they have in a sense, a more reliable expectation for their water supply on any given year. And remember that in our reservoirs, we only have about a year's worth of storage in California. So that's something to remember. Well, one of the real puzzles about the variability of our water supply is the effect of these very persistent droughts. And a lot of you will remember the drought episode that we had in the period from 1987 through 1992 in the state. It was a 6-year episode. It was the longest drought that we've seen in the observational record. But one of the interesting things is that when we appeal to some of these paleoclimate measures, such as in this case tree stumps that are located in many cases in submerged lakes, and in this case this is Mono Lake, which has been drained artificially because of the voracious nature of the Los Angeles aqueduct. It was discovered that there are stumps where there should be 10 meters of water, and those stumps had 80 tree rings in them. Evidence that in the medieval period there were 2 sequences of something like 100-year dry episodes that affected the state. Now the medieval period is not that long ago that we can claim that this was a different climate from today. So that I think this is a warning signal that the amount of precipitation that we've grown to count on in the state is not necessarily what we're going to get. So that's one of the underpinnings of why some fairly exotic research, such as these tree ring studies and so on, actually have a lot of application to what we're trying to do today. Well, I mentioned that there's an El Nino that's developed. You can see this is the trace of the anomalous or departure from normal of sea surface temperature out here in the Central Pacific, which is a region that we know is very strongly influential in the driving the atmospheric circulation engine. And that temperature in recent months has risen to well above 1 degree Celsius over its normal, and you can see its spatial layout here. You also notice that warm water is starting to sort of appear along the west coast. And El Nino, of course, is of great interest to climatologists, not only because it has such a profound influence on the ocean and the atmosphere, but in many cases the bottom line is the fact that it sort of gives us an edge months in advance, more than any other phenomena that we can look at as a climate predictor. And if there's one area that's been driving climate science over the last couple of decades, it's prediction. Everybody wants to know what's going to happen next year, what's going to happen to the next generation, and that's a critical issue. And of course, ENSO, El Nino Southern Oscillation, is one of these phenomena that has a memory and a relatively regular order that provides us a little bit of that view ahead that we need in order to try to make decisions, try to get an edge on just relying on the entire envelope of climatology. And this map shows you in composite over a bunch of historical cases what has happened with El Nino over the United States during wintertime for precipitation. So they're going back to the early 1900s, and they're arraying a set of El Ninos. And the areas that are shaded by green are strongly likely to have heavier than normal precipitation for the period, and the yellow-brown areas are likely to probably suffer deficits. This area of the Ohio Valley and this area of the interior Northwest is an area that is probably having some concern, particularly this area because they've already gone through some dry spells, and of course you've noticed all of the hullabaloo that we've had in our summer periods with wildfires. Well, here's another way of looking at the same thing. This is an array of daily flows that we've taken from, in the lower case, this is the southern San Joaquin Valley. The red traces are a set of daily stream flows through the calendar year that occur during El Ninos. The blue traces are ones which occurred during La Niñas, the opposite side of the coin, when the tropics are cool rather than warm. This, on the other hand, is a set of hydrographs from the Clark Fork, which is a river that drains in the Columbia system. And during El Nino, in the southwestern case, there's a tendency for heavy flows, in fact, some floods. In the Clark Fork, in fact, those heavy flows are more likely to happen during La Niñas. And this map is just another way of seeing this same picture in sort of landscape view, where the red shading says that you're more likely to receive heavy precipitation during El Nino than La Nina, and the blue is the opposite. So we're in the part of the world that is favored in sort of a water supply sense by having a warm event in the tropical Pacific. And of course, in the last few years, we've gone through a cool tropical Pacific phase. And so this warming that we've seen over the last 9 months or so has been a really interesting change of events. Now, one of the truth in advertising parts of this story is the fact that El Nino is not a guarantee. So what, for example, if we collect a bunch of precipitation stations over the south coast, as shown here in the bottom, and we just array their annual precipitation, which is shown vertically here along the scale, and we compartmentalize these by 3 different categories: El Nino, neutral, that is when the Pacific basin is kind of normal, and La Nina, that's the blue colors. We notice that the La Ninas are generally relatively light in terms of the amount of precipitation. Here's the average right along here. So most of these are either normal or below. The El Ninos have a lot of heavy events, but in fact, they're not void of dry cases. And of course, the neutral years essentially is almost climatology. By the way, when we go to the water-bearing part of the state, farther north, you notice that this is pretty much a no relationship sort of picture. There's really nothing to be gained in the northern part of California by knowing that it's El Nino. It's kind of between this heavy part that occupies the southwest and the dry part that happens in the northwest. And it's not that El Nino doesn't have an influence on Northern California, it's just that every event is different. Well, here's in making these talks, we were asked to provide a little bit of historical context. And this is a picture of Jerome Timaeus, who was the founder of the Climate Research Group at Scripps. And Chip had a hand in this because he was involved with the NORPAX project way back, and Jerome worked on that project. But Timaeus was formerly the chief of the Extended Weather Forecasting Division at the National Weather Service. His career actually went back to the 1940s there, and he had quite a long and very interesting career, because that was the period when meteorology was essentially developing into a science from more of an empirical sort of set of rules. And it was the development of the modern weather models and so on. And Jerome was the guy that was taking weather and sort of asking the question of how far out can we predict? And if you look at his publications, you can see the seeds of 3 days and then 5 days, 30 days, 90 days, where he was starting to venture out in sort of tackling this problem of prediction. To him, that was the central theme. And I worked under Jerome when I was a fledgling here, and we used to have this ritual at the beginning of every season where we were preparing a forecast. You see, he never lost that habit. He came here to Scripps, and he started this series of experimental forecasts, which in fact were really not experimental, they were operational. He did them every season, and kind of a thorn in the side of the Weather Service, he would release them to the press, and they would pit one against the other, of course. There's no reporters in this audience, so I can talk fondly about the press. But Jerome used prediction as kind of a view of the weather, because he had a very healthy curiosity about what was going to happen, and he was always looking at things not only from the context, like many climatologists, of what did happen, but as to what is going to happen. So he was a very effective exponent of climate research and forecasting, and he came here beginning in sort of a sabbatical basis in 1968. He eventually landed up here in 1972, started this group. In fact, some of that group is still here. Tim Barnett is still working, John Rhodes, myself. So we owe a lot to Timaeus and sort of the foundation that he laid. He came to Scripps to sort of explore a central hypothesis. And the hypothesis that he was sort of working on was, does the heat that's accumulated in the upper layers of the North Pacific Ocean have the power to influence the weather that affects the continent of North America? So we know that the weather comes from west and sweeps towards the east, and of course he was asking the question as to how the atmospheric circulation would pick up that influence over the large expanse of the Pacific Basin, which in northern latitudes is the biggest game in town, and how does it affect the weather here on the continent, and furthermore, could he exploit the knowledge of what's going on in the sea surface temperature and make a prediction for the next season or the next year and so on. And he essentially spent the next 20 years working on that idea. Now, one of the things that in sort of fairness that I think Timaeus missed was the fact that the tropics turned out to be the biggest gorilla out in that zoo. The tropical oceans are now well known that they have a much larger impact than do the extratropics, but he came from a culture in which, when you think about it, he was watching the huge variability in the jet stream that was discovered during the sort of evolution of aviation weather. And he was a middle latitude synoptician, and this was the card that he played, and it was still an interesting one, and actually still remains an interesting one. It's just that he did not recognize the strong influence of the tropics. This is the picture from one of his 4 volumes of collected works. This is actually the circulation and the sea surface temperature anomalies during one of our fantastic winters, historically 1969, in which there was lots of activity along the west coast. But the interesting thing that Timaeus started uncovering when he came here was the fact that there was this intimate connection between the circulation in the atmosphere and the underlying imprint in the ocean temperature anomaly field, the departures from normal. So that when you got these northerly currents in the atmosphere, generally the water was cold, and when you got southerly currents, the water was warm. Okay, well, I want to fly through a couple of more applications, and then it's time to get off the stage here. But one of the things that we're doing now is we're taking climate to some other problems. And one of the problems that we're working on here in the state is this human health related problem of encephalitis, which is a vector-borne disease. It's carried by mosquitoes. In fact, it's carried primarily by one female mosquito, the tarsalis, that actually the main parts of the chain are birds and some mammals, and some sort of dead-end parts of the chain, so to speak, are horses and people. And of course, encephalitis doesn't happen too often because the public health mechanism is pretty good at kind of preventing it. But with the specter of West Nile virus and some other possibilities on the horizon, this sort of study becomes pretty interesting. Now, it turns out that in California for decades now, we've had mosquito control districts, and this is Actually, the driving force behind this particular study is Bill Risen, who's holding a night's catch of mosquitoes from the Kern County area in this jar. He's an entomologist from UC Davis, and it turns out that mosquito districts have been collecting mosquitoes now for, in some cases, back to the 1950s. Now, one of the problems that we have in trying to make links between climate and other stuff, whether it's economics or whether it's wildfire or whether it's human health, is that we need data. It's like Sherlock Holmes said to Watson, he said, "I need data." And this is one of those cases where we actually have years of data that we can interrogate to explore whether there is a climate connection. And when you think about it, mosquitoes probably should have a climate connection because they breed in water and their metabolism and their reproductive processes are governed by temperature. That's pretty well known. So that if the temperature is above or below normal and whether there's water standing around or not, should have an influence on the abundance of mosquitoes in the state. And that's what we're looking at here. We've taken a number of these mosquito records that have been collected by districts around the state. And by the way, this is a huge effort getting this data together. If you can imagine a bunch of old file drawers with paper, remarks and numbers and stuff like that. And one graduate student up at a lonely lab in Bakersfield that's kind of collecting all this stuff and quality controlling it and so on. And that's sort of the drill that has to happen with a lot of these activities in order to make some progress. So this is the correlation between moisture received in the California area in wintertime and the mosquito abundance at a set of these mosquito traps. Mosquitoes are trapped by light, by the way. In this case, they use what's called a New Jersey light trap to collect the mosquitoes. Another problem with this is that because cities have grown and there's more light in sort of an ambient sense, that's kind of a contaminant that we've had to try to contend with in looking at this record. In other words, is this change because of climate or is it because of cities? And we're constantly fighting those sorts of battles. But the signal emerges. The red colors indicate significant positive correlations, and you can see that there's definitely, I would say, without a doubt, a climate connection. And we see it not only for the wintertime precipitation, but when we do an independent look at springtime, we see pretty much the same pattern with some curious negative correlations up there in the Sacramento Valley region that we're still coming to grips with. Well, we went through a really interesting event just in the last couple days here in California where we actually had some pretty severe fires in Malibu, and they were brought on with this really heavy and intense Santa Ana episode. This is a routine forecast map that's generated here at Scripps experimentally by the Experimental Climate Prediction Center, and they produce what's called a fire weather index. The red shading on that index is the highest fire danger, and you can see this real heavy flow, strong flow, and the dry conditions that are prone to fire over the California region. These are a few clips that we got off from the web during this event. This was actually a forecast that ECPC does this out to days in advance. This is the synoptic setting that produced this event. Here's California and the West Coast here. Sorry for the poorness of the graphics. The contours of the flow at the 500 millibar level, about 5 kilometers aloft in the atmosphere, and you can see that the jet stream and the atmospheric circulation is very contorted right now. It's going way down over the eastern Pacific and way up over western Canada. And there's this little feature down here of this closed so-called cutoff low. The air is circulating in a counterclockwise sense around that low, and we're getting these north to east winds around that low. This is another picture of the same thing. That's sort of a vestige of this flow that, and it's kind of resident and not moving very fast over here in California. This is the satellite image that's associated with this as of yesterday, and you can see how the clouds are sort of oriented around this circulation. This morning there was actually some thunder and lightning as this low is developing and sort of making its presence felt here in the southwest. And it's interesting that as I think one of the things that's happened in my career is that because of the wealth of data and the development of computational capabilities and more and better ways of looking at the atmosphere and the ocean, is the fact that we can look at not only sort of broad-scale views of climate, like the months and the seasons that Timaeus was looking at when he first came here, but we can also look at these extreme events, like Santa Ana. And when you think about it, the extreme events are really a very important part of the climate. They happen rarely, but they have huge impacts. They're kind of like geology, you know. Nothing happens for years and years, and then you get a big flood, and you get lots of sediment that's deposited in erosion and so on. Well, in a sense, the same thing happens in climate-wise, and we have to exploit the data that we have to look at these events. And that's what we're doing here with Santa Ana's by looking retrospectively. This is a set of pictures that Larry Riddle put together that show that, first of all, the climatology of Santa Ana's. It's kind of ironic that we live in a Mediterranean climate where in the wintertime we're supposed to be moist and cool, and in fact we get our driest and harshest conditions actually in the wintertime. And that's because, of course, we can get this cold air that fills the Great Basin and produces this adverse pressure gradient that forces the wind through mountain gaps and produces all this this dry air, which is shown here on this graph. This is meant to show the pressure difference between Tonopah, Nevada, up there in the Great Basin versus San Diego. And when that pressure difference gets to be, in this case, in the positive sense, that is Tonopah high, San Diego low, we tend to get our driest conditions when dew points, as measured here at the radiosonde sounding in San Diego, get to be down at the -10 to -15 degrees Celsius level at the lower part of the atmosphere. And this is a record of how Santa Ana's have kind of come and gone through the period back to about World War II. And one of the measures that we see in Santa Ana's, just like we see in virtually every other record that we look at, is the fact that there's variability, and we would say that this is short period climate variability, and hopefully there's kind of a rhyme and a reason as to why some years have frequent Santa Ana's and others don't. Now, I don't have all the answers to that yet, but that's kind of the premise that we're working under. Another thing that we're working on is we're taking moisture that's accumulated seasonally over the western part of North America here, and we're looking at that moisture in terms of whether it's connected with wildfire activity. And we find that when there's heavy moisture, actually the year before the wildfire season, that's actually favorable for lots of wildfire activity. And when it's dry during the concurrent year, that is, such as it was last summer, that in many cases favors wildfires, indicated by the red shading here. The blue is the opposite sort of correlation. And Tony Westerling, who's actually an economics graduate from UCSD, came here as a postdoc, has worked out a fairly sophisticated statistical forecasting scheme to exploit a data set. Here's another one of those cases where he took all of the federal agencies that collect fire data, Bureau of Land Management, Parks, Forest Service. They're operational agencies. They're always concerned about the next year. They never bother to really organize their data. Tony put it all together in one unified archive, and he's able to build this forecasting scheme out of it. So this is the kind of thing that has to happen. Another thing, I've talked pretty much about moisture here this morning, but temperature plays a prominent role too. And in the West, over the last 50 years, we've noticed a big trend in spring and winter temperatures. This is the spring temperature anomaly, or actually trend, from 1950 through about 5 years ago. And there's this big warming signature with 3 degrees Celsius warming over central western Canada here. It's been a degree or so warmer along our coast. This has led to an advance in what you would call measures of spring, in this case snowmelt-driven stream flow. The red and orange dots, these are all USGS stream gauges, and what we've done is we've identified the period in which the snowmelt starts at each one of those gauges, and the reddish shading indicates that the timing has advanced. It's gotten earlier, and the blue shading shows that it's gotten later, and as you notice here, pretty much they've all gotten earlier. They've gotten earlier by about a week to, in some cases, over 4 weeks relative to what they were back in the 1950s and 60s. And I don't have to tell you how important snow is in terms of our water economy in the West. Snow is a fabulous reservoir when you think about it. It stores the water during the period when the storms are the fiercest and we might have floods. We've got that snowpack that's holding off water from affecting these lower basins. And anyway, the fate of that snowpack is tremendously important. Well, I mentioned El Nino. We also have in the Pacific Basin lower frequency variations. This is a record that goes back to the turn of the century, put together by Nate Mantua, who used to be here and now is at the University of Washington. This shows how the atmosphere and the ocean have kind of ganged up in this interdecadal so-called Pacific decadal oscillation that is an effect of our weather here in the West. That possibly has had a role to play in this warming that I mentioned over the West since 1950. The other thing that, of course, we're really keying on is the fact that we think that climate is warming because of human activities, and using the laboratory of numerical models, it's pretty clear that, well, here we've got a set of models, 7 or 8 of them, and excuse the fuzziness, but this is 1900 and this is 2100 with all of these coupled ocean atmosphere, fairly state-of-the-art models. They're all producing warming because of the emissions of greenhouse gases. They also include aerosols and sulfates in them. And over the West, this is a grid point taken from Northern California, we're seeing warming to the tune of about 3 degrees Celsius by the end of the present century. So a lot of us aren't going to see that, but our children and maybe our grandchildren are going to have to contend with the effects of that. one of the messages here is that we think that this warming is probably a pretty solid concern. In terms of regional precipitation, which is arrayed here from all of these models, this is the present day level. You can see that it is pretty much spaghetti, and that some of the models produce wetter and some of them are slightly drier. So the jury is still out as far as that is concerned. This is a map showing from one of these models that we used here in a collective experiment called the Accelerated Climate Prediction Initiative that Tim Barnett here at Scripps organized to look at water problems in the West. This is the parallel coupled model from NCAR, and its view of the warming that would occur by towards the end of the century over the globe, and you can see how this warming is much more pronounced in higher latitudes than it is in the tropics. Again, in our area of the woods, it was about 2.5 to 3 degrees Celsius. This is the precipitation changes from that same model. Green is wetter, brown is drier. In California, it was pretty much the same. You can see how in our area, if you look at the number of heat waves, this is the May through October period of each year in this model going out to the end of the century. And you can see essentially the expansion of the length and intensity of summer as global warming takes over. I mentioned the impact of snow and the value it has to the states. The western states have been monitoring snow, not as a climate measure, but as a water resources index, going back to, in many cases, the 1920s and 1930s, which, by the way, was brought on to large measure by a big drought that the West had at that point. In many cases, droughts are good for climate research. Unfortunately. This, by the way, if you go through time with this model that I mentioned 2 slides ago, this is a depiction of our April 1 snowpack in 3 sort of decade time slices, 2030, 2060, 2090. The blue shading is essentially the current day levels. This is the Sierra Nevada. This is the coast ranges of the state. So you're seeing this sort of mega watershed that drains into San Francisco Bay in the state, which is our biggest plumbing fixture, so to speak. By mid-century, the red shading indicates that we're down to below 30% of what the present day April 1 snow accumulation is, and you can see that a lot of red shading is starting to appear, and essentially it's moving up the mountain slopes, so that by the end of the century we've lost half of the snowpack. So this is something that we're concerned with, the state is concerned with, and in fact all of a sudden I think many of the western states are concerned with this. In California, this is not only a concern because of water quantity, but water quality. This is the flow into San Francisco Bay from the northern headwaters, the Sacramento part of this system. The green trace is the modern day hydrograph. So this is the water year from October through September, sort of a climatological view. And then the red trace is what would happen in 2090 with this change in the snowpack. And you can see that, well, we don't really lose water. This isn't to say that we've lost water volume. It's just saying that it's happening differently and it's running off earlier. So that this later part of the freshwater inflow to San Francisco Bay has been vastly eroded in the Sacramento part of the system. It's also eroded in the San Joaquin, which is the southern limb of the the watershed. But the San Joaquin is higher. The Sierra slopes upward as we go south. We get the really high area in the south, and it is not as influenced as the north. But the problem there is that the salinity in San Francisco Bay is pretty much directly proportional to that freshwater flow. And with all of the state's water problems, and the bay is sort of a conduit of water that comes from the north and goes to the south. 70 to 80% of our water in the state is accrued north of San Francisco, and about 3/4 of it is used south of that latitude. So that the bay is a huge part of our water conveyance system. So this is one of those impacts that we're really concerned with. The other one is the fact that sea levels will probably rise. And in fact, along our coast, historically, we have noticed that sea levels have been rising at about 0.6 of a foot per century. And this is that record up to this point here. And you notice that it's not smooth, that there's some years where it's higher than it might have been. And those years, by the way, are El Ninos. And then if we sort of extrapolate forward with guesses, educated guesses from these climate models about how sea level will change, rise, over the next century, we might get something like this. And of course, for those people that own coastal real estate and those people that are concerned about, again, the San Francisco Bay area that has a lot of low-lying lands that are protected by levees and dikes, and where they're trying to restore wetlands and putting a lot of resources into that in the current period. Climate information has to be part of that process. And so this CalFed effort, which is a multi-year effort to think about water supply, water quality, and habitat in that region, is having climate now as part of their agenda. Well, final note, which is part of our sort of personal mandate, is the fact that we need more high elevation climate records. That's where it's happening as far as the influence of these temperature changes, because when you think about it, when you drive up a mountain slope, you see enormous changes from the valley to the alpine areas, and they're all compressed into 50 miles or so. If you've ever crossed the Tioga Road over Tioga Pass down into Lee Vining, you see all that change in ecosystem just laid out right before you. And when you look at the distribution of weather stations across the state and you start compartmentalizing them by elevation, you notice that by the time you get up to 7,000 feet or so, they're pretty thin. And that's the area that we're starting to work on in the state. Cheryl's getting edgy because I've talked too long. And thanks a lot for the attention, and I'm impressed that everybody came. Thanks.